Welcome to USHENDRA'S Engineering Tutorials. It's something about a single input, unbalanced output. An important analysis about the differential amplifier and one of the important configuration of a differential amplifier, single input, unbalanced output. Let's see if how the circuit diagrams look like and what are the important derivations. Here, two transistors, transistor Q1 like this, and another transistor Q2 like this. Both the emitters, this arrow mark says these are the emitter terminals, and the transistors are made using common emitter configuration. Both the emitters are short circuited like this and commonly connected to a external resistance RE, and other end of the resistor is connected to a negative voltage minus VEE. So all these arrangements are to obtain the perfect operating point. Here RC to the collector and another RC to the collector. Here it's perfectly connected and connected to a plus VCC over here, and the name itself says single input. So what do I mean by that? It's only one input we have, unlike dual input, single input with only one input. It's a V in, designated as V in, and other end is grounded, and the internal resistance of the source cannot be neglected, R in, right? No one, it's simply V in because we don't have the other one. Another over here, it's the base is grounded, and unbalanced output in the sense the output is collected across only one collector. Let it be from here, V0, with respect to the ground. Output is collected across one of the collector with respect to the ground. This is the configuration, single input, unbalanced output. Before going much deeper into the analysis, some prerequisites. For example, it's connected in common emitter configuration. The current amplification factor beta, more precisely beta AC, will be IC by IB, and will be approximately equal to IE by IB. IC will be approximately equal to IE in case of a transistor. In that sense, IB can be plugged with IE by beta AC, right? Keep that in mind. Yeah, a very important one. Yeah. So reducing this circuit to its AC equivalent. What is that AC equivalent? Here two emitters are short circuited. Let this be this one here. Two emitters are short circuited like this and commonly connected to an external resistance RE, and another end of the resistance is connected to what? To minus EE? No. AC equivalent, we neglect all the DC sources, so it should be grounded, right? So coming this side, transistor is short circuited, and this would be existing like this one. Let it be the emitter, right? I've told you it's emitter 1 and emitter 2. And continuing with this one, what we have is here, it's a source over here, AC equivalent, so AC source exists, V in, and another end is grounded over here, and we cannot neglect the internal resistance of this source resistance, I mean R in exists. It's for the base. Here we have the base, and RC grounded. We have RC, the DC source is grounded, RC, and grounded over here. And the other side, the symmetry, it's an emitter connected to the base, and the base is grounded from the circuit itself. And here it continues with the RC over here, it's RC, and we don't have that plus VCC, even that is grounded. Output is collected across over this point, it's a V0, and now this is our output, V0, right? And on the other hand, we in the AC equivalent, we cannot neglect the dynamic resistance of the emitter junction. Here it appears over here while we discuss about AC. If the discussion is about AC inputs, the dynamic resistance of the emitter junction comes into the picture. Emitter, where is that emitter? Here, these are emitter. Make a note please, it's our emitter. We have the resistance RE, which is known as the dynamic resistance of the emitter junction, and another transistor even that exists are E. Now we have to bother about the current flows. Only one source here, so current will be flowing in this direction. It's a IB1. So for the base one, IB1. Entering into the emitter, it becomes IE1. And after this node here, I'm marking with the blue. After this node, it splits into two currents. Let this be the current through this one be IE, and current through this one be, I'm writing over here, it's a IE2. And after this node, some amount of current will be flowing, that is IC2. In this case, what will be our V0? Output voltage is equal to RC. Here, this is our output voltage, RC into IC2. Writing it again, I'm writing over here important equations. V0 in this case will be equal to RC into IC2. IC2 here. So writing the expression for this loop, the drop for this loop here, from here to here, what we have is V in, the supply voltage V in will be equal to this drop, that's IB1, IB1 R in, plus this one IE1 RE, IE1 RE, and what will be this, plus IE RE. We need the entire equation to be in terms of IE1 or IE2. So this could be transformed to IE1 making use of this equation. So what will be this? And on the other hand, what about this IE? What about this IE we have over here? So IE could be, this current is equal to this current plus this current. So writing over here, it's a IE1 is equal to IE plus IE2, right? So from which we have IE will be equal to IE1 minus IE2. So this could be made use of to change the entire equation in terms of IE1 or IE2. And here IB1 could be plugged in with the IE1 into Rin by beta AC. From here, this one IB could be IE by beta AC, so I have plugged in that with that one, plus IE1 RE plus its RE, don't get confused, and this one with this one, in the sense simplifying it, IE1 RE minus IE2 RE. Please make a note of these equations. And taking out IE1 as common, IE1 is common from this, and this, what we have is Rin by beta AC plus RE, it's RE, plus we have this one also, capital RE, the external resistance, RE minus IE2 RE. Yeah, this is the expression. And in this very expression, when compared to this sum, this RE plus RE, this is very small. Please, when compared to this one, this is very small and can be neglected, practically can be neglected. And this equation takes the form here. This will be, so V in will be equal to IE1. And neglecting this one, we have RE, the dynamic resistance of the emitter junction, plus RE minus of IE2 RE. Guys, let this be equation 1. Let this entire equation be 1. Make a note, please. Now considering the second loop, this one, which loop? Here, starting from the supply voltage V in and crossing all these here, can you see this up to this ground, this loop? So how to write that equations? It's again V in will be equal to this drop. What is this drop? IB1 Rin plus this is a IE1 RE, the dynamic emitter resistance, emitter junction resistance, plus this drop here up to this point. It's a ground over here, so it's up to this point. Don't get confused here. Starting from this supply to this and this one. So we are done with this one. So this, it's a IE2 RE. Guys, once again, we want the entire expression in terms of IE1 and IE2. So what is this doing over here? What does this got to do over here? This can be transformed using this equation. So that will be IE1, taking out IE1 as common from this, it will be Rin by beta AC, right? And plus RE from here, plus IE2 RE. Guys, once again, when compared to this will be very small. Practically, this will be very small and can be, this term can be neglected. This ratio can be neglected when compared to this. Our final expression for V in will be equal to, here it's a IE1 RE plus IE2 RE. Yeah, let this be the expression number 2. One we have there, 2. Make a note, please. So both the equations we have done with both the equations, so we don't need this one. I'm going to erase this one. Please make a note. Both the equations 1 and 2 rewritten again here for convenience. Let's start the analysis from here. Both the equations can be written in a matrix form. How can that be written here? It's a V in and V in a column over here. It's like this, which will be equal to the resistances over here and the currents IE1 here and IE2 over here. And the resistances, this matrix will be Re plus that Re, external resistance, and this will be positive, so negative, it's a minus Re over here, and this Re and this Re comes here. So how to evaluate for IE2? Here we need IE2. How to evaluate for that? Making use of Cramer's rule. Cramer's rule, that will be very convenient for us. So IE2, so this comes as it is. It's a Re plus Re over here and Re, and this entire column comes over here. It's like plugging in V in, and this is even V in, and the determinant of this one, and in the denominator this comes as it is. It's a Re plus Re, and it's a minus Re over this side, and here Re and another Re over here, and the determinant. So simplifying this one, what do we have? It's in the denominator, this into this, in the sense V in into Re plus Re minus this into this, right? So minus V in into Re in the numerator. So what we have in the denominator, this into this, in the sense Re into Re plus Re, and this into this minus this into this. We already have a negative, so that will be plus Re into Re. This is our expression for IE2 here. And going back to that prerequisites, first we have written from the beginning. What is V0? V0 is RC into IC2, isn't it, from the arrangement, and that which will be equal to RC into IE2. Plugging in the value for this one, will be having V0 IE. So V0 will be equal to, going ahead, V0 will be equal to RC as it is, RC, making no mistake. This one, it's guys, over here, this V in Re and plus V in Re minus V in Re gets cancelled. We'll be having V in Re, so we'll be left with V in RE. Here it's a V in RE, and this one, right? In the denominator, it will be taking out RE as common here, from here and here, taking out RE as common, RE. Inside the bracket we have RE plus RE plus RE, so that will lead us to RE plus twice of external resistance, emitter resistance, RE. Okay guys, and the reality is, in practically what exists, what comes into picture is RE when compared to RE is very much smaller than RE. In that case, over here this can be neglected over here, and our expression for V naught will be equal to here, it's a RC and V in into RE upon RE as it is over here, that cannot be neglected here, RE as it is. Inside the bracket, this value is very much larger when compared to this one, so this can be neglected here, so it's twice of RE. Guys, can you see something gets cancelled over here? This RE and this RE gets cancelled, and what else? So which will be equal to, what's that, RE, and we are in search of RC by RE 2 into V in. So actually we are in search of this can be written, right, this by this and 2, nothing, no change, don't get confused, right? So we are in search of the voltage gain AB. Here it's a partition, don't mind. We are in search of the fraction V naught, the ratio V naught by V in, which is equal to what, RC by RE whole by 2. This will be the voltage gain AV which we are in search of. This one, this is the important expression. And can you see, I've written intentionally this, the voltage gain of single input unbalanced output is half of the voltage gain of dual input balanced output. So this is how, this is the reason I've written like this, for a more clear picture. Important expression. Evaluating the expression for IE1 from this very matrix, making use of Cramer's rule, what we have, IE1 will be equal to, it's a first term, so this comes over here. Let me change the color for you. It's a V in over here, this one, this comes over here, V in comes over here, it's a minus RE, this one minus RE, and RE over here, it's this, the determinant of this one for IE1, and in the numerator, in the denominator, it comes as it is, it's a RE plus RE minus RE over here, and it's a RE and another RE over here, it's RE here, right? And what would be the expression for, after simplifying that one, what would be the expression for IE1? IE1 will be equal to, guys, in the numerator, it's a V in RE, V in, it's a RE plus V in RE in the numerator, and in the denominator it's RE into RE plus RE plus, so actually it should have minus, already we have a negative, so that will be plus RE into RE, my expression for IE, and still could be simplified to V in into RE plus RE, this one, and it's as it is, RE into RE plus twice of RE, another simplification, taking out RE as common from all the terms, right? So this is my expression for IE1. So I'm in search of input impedance of the configuration. What is that? We are in input impedance of the configuration. It's a V in input voltage by the input current IB1, IB1 actually, but IB1 can be substituted with V in as it is, V in as it is. IB1 can be substituted with something else from the beginning. We are sticking to something else, right? So IB1 could be IE1 upon beta, going up that it's a beta AC. This is the expression, simplified expression. Now plugging in the value of IE1 over here, we will be having the expression for R in. What's that R in? Final R in will be equal to V in as it is in the numerator, V in, and beta AC upon, what is that, IE, V in, and a small simplification over here. It's a, guys, when compared to this is very small, so we will be having RE, and in the over here it goes up, so we'll be having, when compared to this is very small, so what we have is this will be left and this will be left. So what are the parameters left over here? It's a RE, and inside the bracket this can be neglected when compared to this, so we'll be left with twice of RE. So what gets cancelled over here, guys? V in the numerator, in the denominator gets cancelled, and RE also, the external resistance. So and our final input impedance will be equal to twice of beta AC into RE. Another important expression which you have to derive. Guys, hope you understood this derivation. If you feel it's important, please support me with your valuable subscription and a share. Thank you for watching the video.